The diagram below shows an 8 kilogram cart moving to the right at 4 meters per second, about to make a head-on collision with a 4 kilogram cart moving to the left at 6 meters per second. So they give you a diagram. After the collision, the 4 kilogram cart moved to the right at 3 meters per second. What is the velocity of the 8 kilogram cart after the collision? So as we have these two carts colliding, a situation you should be fairly familiar with, and hopefully you recognize that this collision is a conservation of momentum problem. Remember, conservation of momentum says that the total momentum of the system before the collision, pi, is going to be equal to the total momentum of the system after the collision. Well, the most difficult thing about these problems is really just setting up your equation. Once you have your setup, the math itself won't be too difficult. So let's look at this. Before the collision, we have two different carts. And so our momentum equation before the collision is going to have two separate momentums, mv plus mv. And let's just set up our initial part of the equation first before we come back to the final. So mv plus mv, we've got our 8 kilogram cart moving at 4 meters per second, plus this 4 kilogram cart. Now this is important to note here. See that the velocity of the 8 kilogram cart is moving to the right, whereas the velocity of the 4 kilogram cart is moving to the left. And we need to account for that mathematically. And the way we account for a different direction mathematically is using a negative sign. And so for the velocity here, we'll plug in negative 6 meters per second. That's our initial momentum of this system. Let's look at the momentum afterwards. Oftentimes you'll find that the carts stick together. We're not so lucky in this case. The carts collide and bounce off of each other. So afterwards, the 4 kilogram cart moves to the right at 3 meters per second. Now we said to the right is going to be our positive direction. So afterwards we have two carts. It's going to be mv plus mv, two separate momentums. 4 kilogram cart moving to the right at 3 meters per second. So for our second half of the equation, we've got the 4 kilogram cart moving at 3 meters per second. Notice I leave the 3 as positive, because we said that to the right is going to be the positive direction. What is the velocity of the 8 kilogram cart after the collision? So, plus the second momentum is the 8 kilogram cart moving at an unknown velocity v. And so now we have our equation, right? We've got a bunch of masses, a bunch of velocities. This is a messy equation, but we know every value except for the variable v. At this point, if you find that the units, you sort of get a little lost as they get tangled up, that's okay. You substitute it with your units in. So let's just solve using the numbers here. 8 times 4 gives me, looking at this part, 8 times 4 gives me 32, minus 4 times 6 is 24, equals the 4 times 3 here is going to give me 12 plus 8v. Notice a lot less clutter once we drop the units. 32 minus 24 gives us 8 equals 12 plus 8v. We're going to subtract the 12 from both sides. Minus 12, and I'm running out of room here, so I'm going to bounce over here. Negative 4 is equal to 8v. When you divide both sides by the 8, we get v is equal to negative 0.5 meters per second. 0.5 meters per second, the answer is going to be either 1 or 2, right? 5.5 don't quite fit with what we're doing. But how do we know if it's to the left or to the right? Well, remember, we represent left versus right mathematically using positive versus negative. And earlier on, we said that to the right is going to be positive. The right is positive. And so if we have this negative answer at the end, then the object must be moving to the left. Answer choice 1. Yeah.